Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're evaluating beam deflections using moment area methods. We'll do one last example that illustrates the utility of the moment area methods to find deflections. It's very similar to the example we worked in the previous video, except now we're asked to evaluate the deflection at the midpoint between supports A and B. So right about here, and I'll call that point M. Okay, so I'm going to apply a moment area method in a slightly different manner in order to find this deflection. Let's quickly recreate what we had from the previous video. There's our undeflected line. Here's our deflected shape. Okay, this is the deflection that we want to find this time, which I'll call delta M. I'll draw a tangent from A out to point B, and I don't need to go any farther there than that. This distance is T at B with respect to A. I also will make note of this little distance right here, which I'm going to call T at M with respect to A. Okay? So applying the moment area theorems, I realize that T, or delta at M, is equal to this total distance here, which by similar triangles is 1/2 of T at B with respect to A minus T at M with respect to A. Okay, this will give me the magnitude of that deflection. In order to apply the moment area methods between midpoints, if I rigorously keep track of signs, I'm going to have to account for the tangent line being negative and so on. I think the best way to do this problem is to ignore the signs, and we observe by inspection that the deflection is upward. Okay, so let's also quickly recreate the moment diagram. We said before that it looks like a triangle with a peak out here at point B equal to PL over 3. For this problem, we only need to work with the area between points A and B, so we won't worry about the overhang. We need to find T at B with respect to A and T at M with respect to A. And I am going to recall from the previous problem that the magnitude of T at B with respect to A was 1/18 PL cubed over EI. And please review the previous video if you need to see how that was found. T at M with respect to A will be calculated by focusing on the area between points A and M. That's this area right here. That area has a peak magnitude right here equal to 1/2 of PL over 3, which is PL over 6. We'll have a centroidal distance, or distance to the centroid of that area from point M to that location. Our x bar, or x, is equal to 1/3 of L over 2, which would be equal to L over 6. Okay, so now we can calculate T at M with respect to A, and we'll take the area 1/2 PL over 6 times L over 2, and then we'll take the L over 6 times the centroidal distance. So this is area, and this is x bar. Okay, this computes to PL cubed over 2 times 6 is 12 times 12, 144. And let me, before I forget, add in the EI. Okay, so those are the magnitudes. So now I can put it all together. Delta M equals 1/2 of T at B with respect to A. That's 1/18 PL cubed over EI. And then I have minus T at M with respect to A, PL cubed over 144 EI. Let's pull out the PL cubed over EI. I have 1/36 minus 1 over 144. The least common multiple here is 144. 36 goes into it 4 times. We'll multiply by 4 over 4. Therefore, we have 3 over 144, which reduces to 1 over 48 and PL cubed over EI. And that is our peak deflection. Okay, if you recall from the previous problem, the previous example, the deflection at the overhang was equal to 4 over 81 PL cubed over EI. That's a little bit larger than this value right here. So deflection, according to our calculations, deflection at the end is larger than the deflection midway between the two supports. And based on the sketch of my deflected shape, that makes sense to me. I would expect this cantilevered end at with the same rotation here, I would expect it to bend further downwards. So both of these answers taken together seem reasonable and pass my sanity check. That concludes this video.